Hello everyone, my name is Abhinav Gaur. Welcome to this comprehensive course on simple linear regression. I am a data scientist and often wear a data analyst hat as well when it comes to bringing insights out of data and presenting the story behind it. In this video, we will learn about how to build a linear regression model in Python using the Boston housing dataset. Using the learning by doing approach, I'll explain each step and the reasoning behind it. Whether you are a beginner in data science or looking to refresh your knowledge, this video will provide you with a solid foundation. Let's get started. First, we need to import the necessary libraries. We'll use Pandas for data manipulation, NumPy for numerical operations, Seaborn for data visualization, and Matplotlib for plotting. Next, we load our dataset. We are reading a CSV file containing the Boston housing dataset. Let's upload the CSV file to Kaggle and copy the path of this CSV. You can find this CSV file in my GitHub repository link, available in the description of this video. The code is available in the same repository as well. Loading the data is the first step to building our model. This dataset contains features of houses and their prices, which we'll use for regression. We will be using the read_CSV function from the Pandas library, which we aliased as PD while importing the library earlier. We will supply the absolute path of this dataset and will save it in a data frame named df. We will run this cell, using the combination of Shift and Enter keys, to import the required libraries and the dataset. Understanding the data structure and its contents helps us plan the preprocessing and modeling steps effectively. Let's take a quick look at the first few rows of the dataset using the head function. This helps us understand the structure and content of the data. By inspecting the first few rows, we can see the different features available and get an idea of the data types and values we are working with. First of all, let's check if our data contains any missing or null values. We'll use a heat map to visualize these missing values, which can be done using the Seaborn library. We will pass this function a Boolean expression, that is, df.isNull. If the values in any column is null, then this Boolean expression will return true else false. Using this information, the heat map will highlight any null values in the columns of our dataset, making it easy to see where data is missing. We can see that RM column is having some null values. Let's replace it with the average of RM. To figure out the average value of the RM column, we will use a box plot. We will pass on two variables to the box plot function. One is the column name, that is RM, and another is the data frame name, that is df. The center line of the box plot gives us the average value of the RM column. It seems close to 6.2. Let's impute the missing values in the RM column with an average value that is 6.2. Imputing missing values ensures that our dataset is complete and ready for analysis. Missing data can lead to inaccuracies in our model, so it's essential to address it. Here, we replace missing values with a default value, but other strategies include mean, median, mode imputation, or using algorithms to predict missing values. In this case, we define a function to impute missing values in the RM, that is, average number of rooms per dwelling, column with a default value of 6.2. Through a quick check, we now confirm that the dataset doesn't have any more null values. The next step is to prepare the data for modeling and separate the independent variables or features from the dependent variable, that is the target. Splitting the data into features and target variables is necessary to train our model on the features and predict the target variable. The MEDV column represents the median value of owner-occupied homes, which we want to predict, while the other columns are the features that will help in making the prediction. Thereafter, we split the dataset into training and testing sets using a 70-30 split. Splitting the data allows us to train our model on one subset and evaluate its performance on another. This helps in assessing the model's generalization ability to unseen data. We use 70% of the data for training and 30% for testing. The random_state ensures the reproducibility of the split, that is, we will get the exact similar split by using the same random state number if we rerun it anytime in future. In the next step, we standardize the feature variables to have a mean of 0 and a standard deviation of 1, using the standard scalar function. But why do we even standardize this data before modeling? Well, Standardization improves the convergence rate of gradient descent and ensures that all features contribute equally to the result. It helps in dealing with features on different scales and can significantly improve the performance of the model. We have used fit_transform function with train dataset, whereas the transform function to standardize the X-test data. This is done to ensure that the test data is standardized using the same scale as the training data is standardized by the function. Next, we import the linear regression and cross-validation score functions from sklearn library. Thereafter, we create and train a linear regression model. Training the model on the training data allows it to learn the relationships between the features and the target variable. The linear regression model finds the best fitting line through the data by minimizing the sum of squared residuals. Here we have specified the CV is equal to 10, which means the data is split into 10 equal parts, that is the folds. The model is trained on 9 folds and tested on the remaining fold. This process is repeated 10 times, with each fold being used as the test set once. This method provides a robust evaluation of the model's performance across different data subsets. The mean square error comes somewhat close to -25. This model iteration is giving us a decent result but definitely not one of the best one. The closer the MSE is to 0, the better the model is. Let's now see what our prediction values are by passing the X-test to the prediction function. Making predictions allows us to evaluate how well our model generalizes to unseen data. By predicting the target values for the test set, we can compare these predictions with the actual values to assess the model's accuracy. Visualizing prediction errors helps us understand the model's accuracy and identify any biases. A kernel density plot provides a smooth estimate of the error distribution, helping us see where the model tends to over or underpredict. The KDE plot is centered around 0, indicating that the errors, that is the residuals, are balanced around 0. This suggests that the model is unbiased, as it does not consistently overpredict or underpredict the target variable. The plot appears to be relatively symmetric, which implies that the prediction errors are evenly distributed. Symmetric errors indicate that the model performs similarly across different ranges of the target variable. The spread of the errors, that is, the width of the curve, gives us an idea of the model's accuracy. A narrower spread means the predictions are closer to the actual values, indicating a more accurate model. Here, the errors are somewhat concentrated around 0, which is good. There are slight tails on both sides of the plot, indicating the presence of outliers or occasional large errors. This is normal in most real-world datasets, but it might also point to areas where the model could be improved. The peak of the KDE plot indicates the most common error magnitude. Close to 0 suggests that most predictions are very close to the actual values, which is a positive sign. To summarize, this KDE plot indicates that the linear regression model's prediction errors are mostly centered around 0, are symmetrically distributed, and have a relatively narrow spread, suggesting that the model is generally performing well. However, the presence of some outliers suggests there might still be room for improvement. This wraps up the implementation video for the simple linear regression model. I hope you found it informative and engaging. Keep practicing and exploring the fascinating world of data science. Happy learning!